Hello and good evening, everybody. This is Obi-Wan Post for Simplex Pachinko. Going to change the settings a bit here. Back to our usual blue graphs. All right. So, there we are. Yeah. So Blainland, like I asked up there, this is just late start quarter, right? It's not like you've been actually missing stuff. Or do I have that mistake? But what's bad? So does that mean, like, you decided to take a break? Or does that mean, like, the school is just out of session for 4 weeks? What's going on? Alright. So what can we do for you tonight? Hmm. Alright. You're gonna need... Boy. Alright, hang on one sec. Let me fix this, because it's acting up again. Alright. Let's try that. Hopefully this will not cut out every time I try to move. If it does, I'm just going to have to go back to Corsair's website and yell at them. Alright, so the schedule, the timing of everything's kind of screwing everything up. Alright. So it sounds like you might need a refresher on how to do summation notation and all that. All right. Well, I'll try to get some help for it. Hey, you thought that last semester and you managed an A in Calc 2, so not to call you out, sorry. All right, so all right, well, we'll start working on it now, and then in a few weeks, if you got it started up again, then we'll talk more. We can make it work. And again, that Discord channel. Alright, discord.gg/homework is the channel that I sometimes somewhat help out with. Not very often because I got a lot of other stuff to do right now, but occasionally I'll pop in and do other stuff, and there is a lot of other people who are willing to help out. As long as you don't expect a 100% answer right that second, and you're willing to play a few games like I do here, where we try to help you understand things at a pretty deep level, then, yeah, it's going to work out all right. All right, and that's for anybody else who wants in too. So, yep, and they help out with all that upper level stuff too. So there's a channel for like upper level math. That's probably where you want to be. All right, so for sequences, what we've got is a series of individual terms. Your individual terms make up a list of elements, essentially making it a set. This is going to reflect some sort of pattern. The ones that we care about usually do. And also it is indexed by the subscripts. So here we have all these subscripts, term 1, term 2, term 3, term 4, all the way out to term n. And if it's a finite sequence, generally it'll stop with term n. And if it is an infinite sequence, it will keep going on. So when you index with these subscripts, again, we're just saying which number term are we on. All right, so typically if it has a predictable pattern, it's going to look something like a sub I is equal to 3i minus 7, or something like a sub I is equal to a sub I minus 1 plus 2. So something like this. It can be literally anything. So if a sub I is equal to a function of I alone, then this is what we call a explicit, there we go, sequence. And if a sub I is going to be a function of I, or a sub any term we've got, 1, a sub 2, all the way up through a sub I, and this is what we call an implicit sequence. So explicit will be defined by an outside term. And implicit sequences are going to be defined by terms within the equation, or within the sequence. So when you see an implicit sequence, typically you think something like Fibonacci sequence, where the nth Fibonacci term is equal to the n minus 1th Fibonacci term plus the n minus 2nd Fibonacci term. So in this we have f0 is defined as 0, f1 is defined as 1, and then from there it just goes. So f sub n, where n is going to be defined as going from 0 to infinity. Promise I write mathematical notation all the time. N's going to go from 0 to infinity and belongs to integers only. It's not good notation. So f of n as a sequence is going to be 0, 1, 1. Right, add the previous two numbers to get the next one. So 0 and 1 add up to be 1. 1 and 1 make 2. 2 and 1 make 3. 2 and 3 make 5. 3 and 5 make 8. 13, 21, 34, 55, 89, and 144. Almost. All right, and then and then this keeps going on, so it doesn't end. Yeah, can't sneeze. Looking at a light source usually helps, so I was thinking that might hurry it along, but nope, it's just going to stick around for a while. Hate that. So if you're saying that it's series and sequences, then the answer is yes. It also depends on what your teacher likes. So the indices, I usually don't like using I, partially because of the whole I is the square root of one thing. And in this case, it isn't. It is an indexing variable, so it stands for something completely different. Secondly, there's so many more letters to use than, I is kind of hard to draw consistently, the exact same every single time, and it's got a dot above the top. So oftentimes I'll usually use K. So the K is going to go from 1 to N. K is going to be our indexing variable. Most of the time, your indexing variable is either going to be I, J, or K. It's just kind of what we picked. Okay, so for explicit sequences, these are defined by outside terms only. And so this is specifically going to be the indexing variable. So in this case, we used I, but use whatever you feel like. As long as you define it ahead of time, nobody's going to argue too much. Your mileage may vary. Your teacher might complain. Who knows? Hopefully not. All right, and whereas an implicit sequence is something like this one, where Fibonacci sequence is defined by the terms within the sequence. So here, f sub n is going to be equal to f sub n minus 1 plus f sub n minus 2, which are telling us that those are terms that come before the one we're on. F sub n is the one we're trying to figure out. Take the previous two terms, add them up. Whereas for an explicit variable, our explicit term, we're getting a function on I alone. Anybody else not singing live in their head right now? No, just me. So an explicit sequence would be something like a sub I is equal to 3 times I minus 7. This is pretty powerful because it allows you to just skip to whatever variable or whatever term you want to get. So you find the ith term. Super easy. So if I want to find the ith term, oops, in an implicit sequence, the problem is that if I have something like a sub I minus 1, I need the previous term in order to figure out this next term. So if I want the 100th term, then I need the 99th term. If I want the 99th term, then I need the 98th term. And it keeps rolling on backwards until we finally get one that we know. And then we're just going to have to, in this case, add 2 to get to the next one and the next one and the next one. This one's nice and easy because it's a predictable pattern, right? If you just want to add a constant to it, cool. We know how to do that. That's a linear function, right? Our slope is constant. But then the problem becomes if you've got something like the Fibonacci sequence, where you take the 2 previous numbers and add them together to get the next one, there is no explicit sequence form for the Fibonacci sequence. So pretty much, anytime you have an actual function of I for your explicit sequence, you're probably going to be able to create an implicit sequence based on it. So what are you doing from one term to the next? What are you adding? What are you subtracting, multiplying, dividing, whatever? Just about any function you'll be able to get from one to the next in an implicit sequence. But if you have an implicit sequence and you want an explicit sequence, there's no guarantee that you're going to be able to find it. So it makes it much more difficult in that respect. Alright, so the ones we look at in pre-calc are things like a sub I is, you know what, I'm just going to use k's because I like k's better. Alright, so a sub k is equal to a sub k minus 1 plus d. Or more accurately, where does this come from? It's a sub k minus a sub k minus 1 is equal to some d value. So the difference between these two terms, and in fact any two terms on this sequence, are going to be a constant value. Now here's the other thing, right? This one is equivalent to a sub k minus a sub k minus 1 divided by k minus parentheses k minus 1. In here, right, this would be negative k plus 1, and k minus k ends up subtracting out. So this is just a sub k minus a sub k minus 1 divided by 1. So that is this here, and this is the common difference between the two things, which is also known as the slope. So we have this slope here, d. We call it the common difference because it's going to be the difference between all of the individual terms of the sequence. So a sub 1, a sub 2, a sub 3, all the way out to a sub k minus 1, a sub k, a sub k plus 1, and then continuing on out. Right, the common difference between all of these is going to be that d value. Doesn't even matter how far into the sequence we get, it's always going to be that same common difference. That's not x. Right, x is a continuous variable, so we're not going to use that. We're going to use k and then a sub k. So if we want 5, 6, 7, 8. And a sub k is going to be -3. I always hate this part. -7, -11, and -15. Then we're going to do the thing. We're going to look at this and say, okay, what do we have for all of these pieces? Well, here, to go from -3 to -7, we're subtracting 4. Same for all the rest of them. You have to make sure that it's consistent, otherwise it just doesn't work. All right, 5 to 6 is +1, 6 to 7, 7 to 8, all +1. Cool. So then this is our D value. It's going to be -4 divided by 1, or just 4. -4. Really. Okay, and now we can pick any particular point that we want to represent one of our values. I'll say it's going to be, our a sub k minus 1 over k minus 1. Not over, but the k minus 1 comma a sub k minus 1 term, we're going to replace that. So d equals a sub k minus a sub j, just something different. I don't care. Nope. Over k minus j. All right, I'm going to pick one of these pairs out of here. So let's just have it be 6, -7. Have those go in for our j and our a sub j. So this is going to be equal to a sub k minus a sub j is -7. And then on the bottom, k minus, well, no, that's not -7. Wow. All right, k minus 6. And d is equal to -4. So if I move this and multiply it over, I'm going to get a sub k plus 7 equals a -4 times the quantity k minus 6. That should look familiar. Very, very, very familiar. So this is point-slope form. Point-slope form is entirely based on the slope formula. All right, and if we feel like it, we could also say that down here, a sub k is going to be equal to -4 times the quantity k minus 6 minus 7. So either formulation of these is perfectly acceptable. The bottom one obviously gets you probably a fewer marks with the high school teacher, because They'll want everything in terms of, or they'll want everything solved for a sub k in terms of k, I'm sure. As far as I'm concerned, it kind of depends on what you're doing with it. Alright, so when a sequence has a common difference like this, that's then going to lead this to the major property of an arithmetic sum. Not sum. Sequence. We're not doing sums yet. Alright, so this is an arithmetic sequence. It has a common difference, which we can find by subtracting any two terms which are next to each other. So any subsequent or consecutive. Any two consecutive terms in the sequence, you can subtract them and get your common difference. Or you can subtract wherever they are in the entire sequence. So here, doing our a sub k and a sub j thing. A sub k minus a sub j over k minus j. Wherever they are, you just say, okay, my two terms, I'm plugging them into this equation. It's the slope equation. No surprise there. And then that's equal to your common difference, which is your slope. So d is the slope. And again, you can make a linear equation out of this. So a sub k is equal to -4 times the quantity, k minus 6 minus 7. If you want to multiply all that out, then this is going to also be a sub k is equal to -4k plus 24 minus 7. It's going to be a -4k plus 17. So we can determine which form we want. It doesn't really matter, especially in this case. And again, we have our implicit form, which is up top here, showing us that we can use the difference between two terms to get a constant term, or we have the explicit form down here, which is linear. All right, so we can do all the same stuff with linear functions as we can with arithmetic sequences. And then from here we can also add stuff up. So if we wanted to take the terms that we had here and we wanted to add them up, starting from, let's say, a -3. So okay, we'll go back. All right, so that's 5. Let's see, for 4, we would need to add 4 as we're going backwards up this list. So if we add 4, that's going to be 1. Add 4, it's going to be 5. Add 4, it's going to be 9. This is again 5, 4, 3, 2, and one more. Add 4, that's going to be 13. Okay, So this is going to be our a sub 1. -3, -7, -11, -15, and so on and so forth. Now, if we wanted to figure out, this is again a sub 8. If we wanted to figure out what the sum of the first 10 terms is. All right, let's suggest that we started with this list. It's not going to be hard because in order to get the first 10 terms, all we have to do 1, 2, 3, 4, 5, 6, 7, 8 is get 2 more terms, which are going to be -18. Oops, 19. Oops. -19 and -23. And then all we'd have to do is say, oh, well, those are the first 10 terms, so just plug them in the calculator. That one plus that one plus that one plus that one. That's all well and good. But I'm going to use it as an example to do something more difficult because we want the thing that's going to be more difficult to work every single time that we come across something like this. And when it does, that's going to allow us to take this kind of shortcut instead of having to do a crazy amount of work. Okay, so it's going to be easy, but maybe a little tedious to try to plug it into the calculator. What about the sum of the first 1,000 terms? So clearly, this is going to take longer. Right, so this is extremely hard and extremely time consuming for doing stuff by hand, even doing stuff on a calculator without having some sort of like regimented way of doing it. Telling the computer, telling the calculator to add up all these digits is just going to take a really long time. So instead, what we can do is be clever about it and say, all right, look, we're not going to just start plugging these things into a calculator because the first 1,000 terms are going to take a really long time to plug them all in. So instead, what we can do is come up with a method that was the one that Gauss used in Germany in the 1800s when he was at school. 18. Carl Friedrich Gauss. (1777 to 1855). So in the late 1700s, he was in school. In the 1800s, he was pretty much, yeah, done with whatever they had available to him at college. Yep. So Carl Friedrich Gauss came up with this method independently of everybody else who had already known that it existed for a long time, at least the mathematicians did. So he was tasked with adding up the first 100 integers. His teacher was giving him some busy work because he was disrupting the rest of the class. And about 5 minutes later, he came up and the teacher said, "You have a question?" And Carl said, "No, I'm done." And it was that point that the guy knew that he was probably in for a lot of pain at that point. Alright, I am redeeming my own thing. Dost thou e'en hoist? So, Gauss decided that adding up just all of the individual values, 1 to 100, 1 plus 2 plus 3 plus 4, was stupid. And so he was going to need a much simpler way to get the sum of all values 1 to 100. And so he had come up with this idea that what we really need is something that's going to be the same. So in the integers, we have 1, 2, 3, 4, 5, 6, etc., all the way to 96, 97, 98, 99, and 100. He needs to add all these things up. I should have put pluses in between. Oh well. I'm not changing them. Well, he decided that the easiest thing to do would be to take all of the numbers in his list, and he noticed that 1 and 100 add up to the same thing as do 2 and 99, and 3 and 98, 4 and 97, 5 and 95, 96, etc. So all of them add up to the same values, namely 101. So all of these things add up to 101. Then he said, how many times do we see 101? Well, in the middle, right, we end up with 50 and 51, which add up to 101. So then we take all of the lower values, 1, all the way through 50, and that gives us the number of numbers that there are, or number of 101s that there are. So there are a total of 50. So then 101 times 50 is going to be 5,000, because again, this is 50 times 100, and then 50 times 1 is going to be 50. So 5,050 ends up being the answer for this. Only, wait, hang on. Yeah, that'll work. Okay, so either, I kind of did it the other way. How many pairs were there? We counted up by just taking all the smaller ones, then we get to 50 and 51. So there are 50 there. That's what that's going to be. 5,050 is the total. The other way of doing it was saying, okay, I've got 1 plus 2 plus 3 plus 4, etc. 97, 98, 99, 100, summing them all up. And what we can do is take the number line, flip it around, and drop it underneath, so that we have 100 matching with 1, 99 matching with 2, 98 matching with 3, 97 matching with 4, etc. And 4, 3, 2, 1. So when we go down here, we end up with 101 plus 101 plus 101 plus 101, which is the same as we had before, but now there are 100 of them, because we went from 1 all the way up to 100 in doing this formulation and doing these sums. So now there are 100 101s. Except we only wanted to find the sum from 1 to 100, and now we've got 2 lines on which they exist. So we can divide the whole thing by 2. So Gauss realized in this case, It's nice and easy. You have a whole bunch of terms that are going to add up to 101, and then again you're just counting what your index is to get how many of those 101s are going to show up. So 101, or sorry, 100 101s are going to exist if you do this. Take the sequence you want, flip it around and drop it underneath. And if instead you fold the sequence over, you get this one here. So we bind one side to the other. So this ends up just being all the same stuff. It's 50-50, 5,050. All right, so then the question becomes, okay, that's great and all. Now, what about a just random arithmetic sum? So the one we have up above, for instance, where a sub k is defined by negative 4k plus 17. Does it work for that too? And the answer is yes, actually it does. If we look at the simple example, 13, counting all the way down to negative 23, then what we're going to see is, again, we can fold the number line in half here. All right, 13 is going to then match up with negative 23. So what is 13 plus negative 23? Well, that is going to be negative 10. So for 13 plus 9 plus 5 plus 1 plus negative 3 plus negative 7 plus negative 11 plus negative 15 plus negative 19 plus negative 23. Right, we're off the chart here. So shift this over just a little bit. So again, we're going to add our 13 and negative 23, and we get a negative 10. Our 9 and our negative 19. Notice they're the same number again when you add them up. Positive 9 minus 19 is going to be a negative 10. A 5 and a negative 15, a 1 and a negative 11, and a negative 3 and a negative 7. All add up to 10. A negative 10. And we have 1, 2, 3, 4, 5 pairs, because again, we've now bound the left and the right side. We've essentially folded them up, so we only have 5 in each half sequence, which all add up to negative 10. So negative 10 times 5 is going to be negative 50. And again, here we got 5,050 for that one. Or that one. Negative 50 for this one here. Okay. And again, if we double it up, we're going to end up with 13 minus 23 is our first and our last. Did I add something incorrectly? Alright, so a 13 and a negative 23. A 9, negative 19. 5, 1, negative 3, negative 7, negative 11, negative 15, negative 19, negative 23. And negative 19, negative 15, negative 11, negative 7, negative 3. 1, 5, 9, 13. Again, in this case, we end up with a negative 10. Negative 10 multiplied by 10 numbers, but then we're divided by 2 because we only want one of the sums rather than 2 lines of sums. So again, negative 100 over 2 is negative 50. So either way we go about this, we're agreeing. All right, so then the challenge, right? Add up the first 1,000 numbers. Well, let's do it in general. So what have we figured out for this pattern? It looks as though we're taking the first number and the last number and adding them up. Okay, and then every other pair that we get is all going to be the same, right? Because they exactly add up to the same number. It's a nice graphical way to do this too, but all right, so algebraically what's going on here is we're saying that the sum of the first n terms of an arithmetic sequence, so this is what's called a partial sum, specifically the nth partial sum of a particular sequence, is going to add a sub 1 plus a sub 2 plus dot 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 all the way out to a sub n minus 1 plus a sub n. All right, it's going to stop there, whatever it is. In this particular case, right, s sub n is trying to look for a formula, essentially. So what we did, again, was we added our first and our last term. So our first term is a1, our last term is a sub n. So sum up a sub 1 plus a sub n. Then we're going to multiply by the number of terms there are. So this was either, we could think of it as term 1 all the way through term n. So 1, 2, 3, 4, 5 all the way up to n means that there are n terms. Okay, but that's going to be our second option up here, which is going to say, well, we also just double count it because we put these things next to each other. So divide everything by 2. Okay, so that's this one here. The one up top does the same thing, but it's in a different order. We're trying to say here, take 13 and negative 23, add them up, but then, since we're binding first to last and then pairing them off like that, we end up with one term. Nope. We could end up with one term in the middle, right, if it's an odd number of terms, and that's fine. It'll take care of itself over all of this. All right, the other option is that we focus on this one here. We pair off toward the middle, and then the number of times that we're adding this up is going to be n divided by 2. So we end up with 1, 2, 3, 4, 5 distinct lines that are going like that. Out of 10 possible terms. All right, so this is what this gets us. We have this formula, s sub n is equal to n times a sub 1 plus a sub n all over 2. So if we focus in terms of this is n over 2, that way, n over 2, then that is half as many terms as we see here on the page. If instead we focus on trying to get we could focus instead as the 2 being part of this term here. a sub 1 plus a sub n over 2. And interestingly enough, right, this is the average value. So if we were to just take a sub 1 and say, if this function is increasing, take a sub 1, which is low, take a sub n, which is high, and use a sub n to fill in a sub 1 until they're equal. Right? It's an average. So add up the two things, divide by the number of things you have, or add up all the things and divide by the number of things you have. So averaging a sub 1 with a sub n, we get a sub 1 plus a sub n over 2. So there's kind of two ways you can work on that. Okay. So for the example we were doing, this is going to say that the 10th partial sum for this is going to be equal to 10 terms, right? N is 10, multiplied by a sub 1 was negative 23. No, well, it was 13 technically. Doesn't matter which way you go, because again, a sub 1 plus a sub n or a sub n plus a sub 1, it's gonna all be the same. So a sub 1 is 13 plus a sub n is negative 23 all over 2. We already know this is negative 10. So this is going to be 10 times negative 10 all over 2. This is going to be 5 times negative 10 or negative 50. Ah, boy. I apparently have some ads, so I'll just hang on to that for a minute. All right, so that's that. We now have a hey Mogus. We now have a formula which is going to allow us to get the partial sum of any arithmetic sequence. So if it's an arithmetic sequence, we can then say that this is going to be S sub 1000 because we wanted the sum of the first 1,000 terms in this particular sequence. Okay, so the sum of the first 1,000 starts with 13 again. We want 1,000 of them, so n is 1,000. 13 is a sub 1. A sub n is going to be the 1,000th term. Well, good news, we do have an explicit form for this. Next question, do we write it down? Yeah, right. This is it. So a sub k equals negative 4k plus 17. We want what happens when this is 1,000. So negative 4,000 plus 17. So 3953. Negative. All over 2. In this particular case, I'm going to actually hold on to 1,000 because that's an easy number to multiply. And this is going to be equal to 13 plus a negative 3953 is going to be a negative 3940. All over 2 is 1,000 times a negative 1970. So this is going to be a negative 1,970,000. Double check me on that, but yeah, I think we're good. So this is going to be the sum of the first 1,000 terms of that particular sequence. which was a sub k equal to negative 4k plus 17. All right, Amogus, you got anything for us? I'll keep going with series and sequences otherwise, but... Nope, all right. I'll gladly keep going then. Oh, it's really hot in this room. Is the air going? Hang on. All right, turn on the air vent right next to me. This is going to be a lot nicer in about a minute. It's getting so hot in here. It's got to be at least 80. Fahrenheit, obviously. Okay, so this is how to find sums of sequences for arithmetic sequences, and so we call that a series. So in this particular case, we've got the sum of the first 1,000 terms. What we could have done was listed in summation notation. Nope. Trying to sneeze, and it's not working. Anyway, k goes from the first index term all the way through the 1,000th index term, which starts with 13 and ends with negative 3953. Then on the inside here, we get the explicit form for this particular sequence. If you don't have an explicit form, you cannot write the explicit form of the sequence. So what you would say is just, I've got a sub k here, and my a sub k is defined this way. Do it somewhere else. In this particular case, we do have a nice explicit form for it. We just wrote it. Right, so the sum as k goes from 1 to 1,000, sum up all of the terms that look like, where'd it go? Negative 4k plus 17. And again, that's going to equal 1,000. All right. So then, once we get past all that, the other major type of sequence that we look at are what are called geometric. Right, and this is arithmetic. Series. So series is when you add up the terms of a sequence. Sequence is just when you list them. So a geometric sequence is one in which the ratio of two successive terms will always be equal to some value, some ratio, or some constant multiple. Okay, so either the ratio of two successive terms is equal to a particular number, or a sub k is going to be equal to r times a sub k minus 1. Take the previous term, multiply by a number, and come out with the next term. So in what sequence, or in what functions from the original formulation have you ever seen this sort of thing? So start with a number, multiply by a certain amount at every step that we move. So this is going to be k and a sub k. Let's just do the same sort of thing. So 5, 6, 7, 8. And let's keep it easy. So 128, 256, 512, and 1024. All right, powers of 2. So it makes it pretty easy to work with here. Here, as we go down the list, you'll notice that we're not really, well, we're not adding the same thing to get from one step to the next to the next. So unlike a linear function, right, as our k values increase by 1 every time, over here we've increased by a 128, we've increased here by a 256, we've increased here by a 512. We've increased from here by 128. We've increased from here to here by 256. All right, if we kept doing this, next term's 2048. To get to it, we'd have to add 1024. And to get from 512 to 1024, we'd have to add 512. This was one of the first things that I ever noticed about like patterns of numbers is when our teacher gave us a bunch of tables to then say, here's a bunch of rules that you can get. Here's a, you know, here's the inputs and outputs for something. So it wasn't even in terms of inputs and outputs, because this was like 5th grade, 6th grade. So what we had to do was we had a table of values, and then we just had to figure out what the last one was. So in this case, it would have been like, you know, k is 5, 6, 7, 8, 9. And you have all the corresponding values here for a sub k, 128 through 1024. And then you had to figure out that the last one's 2048, something like that. So there's just a bunch of them, and they're all sorts of different functions. So we started out with a few that were linear, just like we saw up top here. Where on the left, our k's were just increasing by 1 every time. And on the right, our a sub k's were increasing by a set amount. So I eventually was like, oh, that's kind of cool. You know, it always ends up being something like this. And then we got one that was different. And it wasn't the one from below where we're multiplying. It was actually something that looked, roughly speaking, like, 1, 2, 3, 4, 5. We have to find 5. And it was like, 1, 4, 9, 16. And we had to figure out what the last one was. Obviously, it's 25. I would have probably figured out that it was just the square of this number or whatever. But my brain immediately went to, well, let's do the same thing that we did for the linear functions. Let's go in here from, again, 1 to 2, 2 to 3, 3 to 4, 4 to 5. They're all plus 1s. From 1 to 4 is a plus 3. From 4 to 9 is a plus 5. From 9 to 16 is a plus 7. From 16 to this unknown value here, we have here 3, 5, 7. Well, that's just a linear amount, so 3, 5, 7, the next one's going to be plus 9. And then, clearly, backtracking, this is going to be 25. So, thank you, Amogus. Get me back to my actual lifting here. So, right, doing this, we figured out that, well, it wasn't that it was just a simple, like, increase of a constant number, but the amount that we were increasing was itself increasing by a constant number. And so I got kind of interested in trying to find that. That's so weird. It's great. These lo-fis have, random stuff, but they do occasionally have something that sounds like somebody trying to talk to me. And it kind of distracts me because it's like, who's talking to me? It's just in my computer. So anyway, yeah. So this itself is going up by 2 every time, by 2 every time, by 2 every time. So here, actually, the plus 9, or the right, if I went like this, I would have gone to the constant part first, said, okay, everything needs to go up by 2. Therefore, this change needs to go up by 2 and make a plus 9. Therefore, this 16 needs to be added to 9 to get 25. So it's like this reverse engineering. So then I got this thing, and I saw that immediately we're getting the exact same numbers we started with in the first place. And so I was like, well, that's really weird. And again, as it turns out, it is not a polynomial, unlike all the rest of the examples we did. So polynomials have that feature whereby you're always adding either a constant or the rate of change of the rate of change of the rate of change, etc., will eventually be a constant. So somewhere in there, there's going to be a constant. In this geometric sequence, however, there isn't, at least not from an additive standpoint. So our numbers are adding together, but we're just adding what we had to begin with. We're multiplying by 2. Okay. So again, plus 1 here. Turns out this is going to increase by a certain amount. It's the amount we started with is going to increase and make it a double of itself, etc., etc. So then, in addition to this, I said, okay, well, clearly that's not working for us. So instead, I switched to multiplication and it worked great, right? So you get 5, 6, 7, 8, 9. 128, 256, 512, 1024, and 2048. Again, here we're multiplying by 2, which is going to be the same for all of these other pairs. Right, and then plus 1 on the other side. So this is what's constant. It's the operation multiply by 2 is constant all the way throughout. So that's really what we're looking for. All right, then we can say here, how do we get the stuff on the right-hand side? Well, multiplying by 2 is an exponential function. Now, I think there's a way to get it the same way we did the common difference up here. Kind of generalize it and say like, oh, look, it's kind of like slope. Yeah, okay. So if we do a sub k over a sub j, this is going to be equal to r, but the r value is the distance between any two successive terms, the common ratio. And here, the common ratio, again, is only the value between the successive terms. So here, if you have a k and a j which are not successive to each other, then we need to take, just like we did over here, this is r to the first, really. So the 1 here is an exponent. The number of times we're multiplying by this r value, the constant ratio, is going to be represented by k minus 1. So just like up above, with a common difference. Here, a sub k divided by a sub j is going to be equal to r raised to the k minus j. All right, and then we can also say, well, if we wanted this to be j equals 1 to make it the sort of easy version, we can multiply our a sub j back to the other side, make this a sub k is equal to a sub j times r to the k minus j, and then say that we want j to be 1. So let it be the first term. So a sub k is equal to a sub 1 times r to the k minus 1. And that is the basic formula. So a sub k is equal to a sub 1 times r to the k minus 1. Right, and this one here is great for being able to get any particular value anywhere out there in the function or in the series, in the sequence. One of those words. No, it's in there somewhere. All right, so 6 comma 256 can be added in here to do, again, the same sort of thing, to say, okay, a sub k is going to be equal to 256 is a sub 6 multiplied by r raised to the k minus 6. So I like this form particularly because, like I said, you can use any point that you want. Typically for a geometric sequence like this, you'll be given like 2 points. No, you have to be. Or 1 point and the common ratio. Alright, so for a geometric sequence, this is what we get to get any position that we want anywhere along any of these. Anytime that you have a constant multiple, got to multiply 256 by that constant multiple, k minus 1 times to get out to the kth term. Alright, so when we want to do geometric series, now we're talking about adding stuff up. So we want to do an a sub 1 plus a sub 2 plus a sub 3 plus etc. all the way out to a sub n and potentially out further. Alright, this will go off to infinity. Now, all of our individual terms can be brought back and written in terms of a sub 1. So a sub 2 is, for instance, a sub 2 is just going to be a sub 1 times r once. A sub 3 is going to be a sub 1 times r twice. A sub n, we just found a sub k up here. It's the same thing. That's fine. We can just make this a sub k. Right, this is just going to be the expression up here. So a sub 1 times r to the k minus 1. And then, of course, as always, this could go on. I'm going to say for right this second, we want to know what happens just with these. So we'll go with finite at the moment. Okay, and this turns out to be the kth partial sum of this particular geometric series. Start at our first term, a sub 1, and then go all the way to our last term, a sub k. Alright, now, this is not going to get us anywhere. So we have to do something that's a little bit different. One thing that we could do is multiply s sub k by r and multiply it in. When we multiply it through, we get an a sub 1, but it's times an r. Okay, a sub 1 times r squared. Yeah, a sub 1. Well, r squared times another r. What we're going to do, sorry, I just glossed over this. What we're going to do is take s sub k in its entirety and multiply the whole thing by r. So r times a sub 1 over 1. Here we're going to get r times I don't need those fractions. I was trying to think of a good reason, but we don't need them. Okay, so a sub 1 times r, nope, a sub 1 is going to become now r times a sub 1. A sub 1 times r to the first is now going to become r squared, a sub 1. And so on and so forth. And then we get r cubed times a sub 1. Plus going all the way out to a sub 1 times r to the k. Alright, all these terms have been bumped up 1 degree. So now, if we subtract this bottom row from our top row here, oops, on the left side of the equality we have an s sub k minus r times s sub k. And on the right we have an a sub 1. We have a plus a sub 1r minus an a sub 1r. So right? When we sum up all these things, it all drops out, except the first term here, a sub 1, and a sub 1 times r to the k doesn't combine with anything above it. So now a negative negative a sub 1 times r to the k. So this is going to be s sub k multiplied by 1 minus r. So I'm going to be multiplied. No, all going to be added out. All of this stuff is all 0. Here we have the first and last term, a sub 1 minus a sub 1 r to the k. Over we get this 1 minus r to divide through. So s sub k is equal to a sub 1 can be factored out from the top. We're left with 1 minus r to the k over 1 minus r. Alright, so the next part says, what happens if our k value keeps growing and growing and becoming super large? So this is going to just be the limit as k goes to infinity of s sub k, which is this thing, a sub 1 times 1 minus r to the k over 1 minus r. Now the limit is able to pass through almost everything. Everything which doesn't have a k variable. So the only term that has a k variable is that one right there. Notation wise, we often say something like s sub infinity is equal to the limit as k approaches infinity of, and that's not even a good place for it. Okay, so we get a sub 1. We get the 1 minus r at the bottom. This one is 1 minus, and here, this is where we have to take the limit as k goes to infinity. It's not 0. As k goes to infinity of r to the k. So this becomes a point of issue. Okay. Oh no. I was watching some TV earlier. Apparently that just crept into my head. Alright. Man. Okay. Too tired. Need to go to bed. So, not enough coffee. Not enough sleep. Apologies. Man. uh, okay. Wow. On the bright side, does this mean nobody saw it? Nope. Hi guys. Oh. Streamer brain is real. All right. So what value does this thing become? Limit as k goes to infinity of r to the k can have a couple of different ways that this can be dealt with. One is that the value of r, so the absolute value of r, is greater than or equal to 1. There's only two ways. Now let's just do greater. It's greater than 1. So if the absolute value is greater than 1, you have a large number. When that gets raised to the kth value, where it becomes larger and larger and larger, well, sorry, r to the k becomes larger and larger and larger. So this is saying that the limit as k goes to infinity of r to the k is going to be infinitely large. Absolute value of r is equal to 1, in which case the limit of k going to infinity of r to the k is going to be either plus or minus 1 depending on what value r was. It's either 1 or negative 1. So the limit as k goes to infinity of absolute value of r to the k is 1. We'll go with that. In which case, the sum as we keep going out is going to either, if it's 1, just keep getting bigger. And if it's negative 1, well, if it's positive 1, it's a constant function, so it just literally just keeps going like this, and you add and add and add, and it becomes infinitely large. The other option is it's negative 1, in which case the first term adds a value, and then the second term will get rid of that value by adding the opposite sign. And then it flips sign again and adds it back, and then it flips sign again and it becomes 0. So, yeah. The third option is the absolute value of r is less than 1, which is the most interesting one, because the limit as k goes to infinity of r to the k, where r is a small number, is going to be equal to 0. So, s sub infinity only works when the absolute value of r is less than 1. So then we end up with s sub infinity is equal to a sub 1 times 1 minus the limit as k goes to infinity of r to the k, in this case becomes 0 over 1 minus r. So s sub infinity is going to be equal to a sub 1 divided by 1 minus r. Where, again, you have r being a small value, whatever small value that might be. So if we wanted to do a geometric series, let's do one here. That'll work. Right, so if we do this one, this is going to be the sum as k goes from 1 to 8. Let's just add up the first 8 terms of this particular sequence. Okay, that's going to start from some value up there. Alright, one of the things that we can do is just start with this here. So our known value at j equals 6. So 256 times r was 2. Oh, probably should have filled that in back here. Raised to k minus 6. All right, 256 times 2 raised to the k minus 6. All right, so if we plug in the appropriate values into what we've got here, oh, that's nice. If we want to know what a sub 1 is, this is going to be our 256 times 2 to the 1 minus 6, which is 256 times 2 to the negative 5th, or 256 times 1/32nd, right? 1 over 2 to the 5th, or 256 divided by 32. That's what I wanted. Give me that calculator. 8. Right. I mean, I probably should know this offhand, but you know, I'm tired. It's fine. 8 is a sub 1. So when we want to sum this up, s sub 8 is going to be equal to 8 times 1 minus r to the k is going to be 2 to the k value is going to be 8 also, over 1 minus 2 is 8 times 1 minus 2 to the 8th is 256, right? Man. making sure. Over -1, which is 8 times a -255 over -1. This can divide out the negative. And we've got a 2040. And it's going to be S sub 8. Right on. Give me 1 minute here. Be right back. All right. So 2040 as our S sub 8 there. And then obviously we can't do something going off to infinity. If it keeps doubling every time, it's just going to go off to infinity. So what would happen if we start with A sub k is equal to so like 1 times, sure, why not? 1/2 to the k minus 1. So this is going to be, plug in a 1, this part goes away, it's just going to be 1, and then a half, a quarter, an eighth, a 16th. So we want to know what's going to happen when we take the sum as k goes from 1 to infinity of 1 times 1/2 to the k minus 1. So up here, we say that r is equal to a half. So then this is going to be a sub 1 over 1 minus r is equal to 1 minus a half in the denominator. And our a sub 1 is just plug in 1. 1 minus 1 is 0, goes away, that's 1. Or also c above. This is then going to be 1 over 1 minus a half is a half. And then multiply both top and bottom by 2, and we get 2 over 1. So this is also kind of an interesting thing to have happen. So in this particular case, we have an infinite number of terms which are all adding up to a finite value, which seems really weird and all that, but it kind of makes sense. Okay, one more. So if we wanted to find what 0.73826733826 repeated is, right, as a fraction, or as a ratio of integers specifically, simplified. All right, so what we would do is we'd say, well, so the first part here, 73826, which is repeating, is the same as 73826 over 10, 100,000, 10,000, 100,000. Right, so 73,826 divided by 100,000 is 0.73826. Then we're adding to it 73826 again, but this time we're back these 5 digits and 5 more. So that's going to be 100,000 squared plus 73826 divided by 100,000 cubed, and so on and so forth. So this is the sum. This k goes from 1 to infinity, because this has to keep repeating forever, of 73826 over 10,000 or 100,000 and if that's the first term, then we want to multiply by 1 over 100,000 raised to the k minus 1. All right, so for this geometric series, what we can do is say, okay, 73,826 over 100,000 is going to be our first term. Then every subsequent term is going to multiply another 100,000 into the denominator, so that's where this 1 over 100,000 raised to the k minus 1 came from. And then that means that a sub 1 is this, r is this. When you plug it into s sub infinity, we end up with 73,826 over 100,000 up top, and on bottom 1 minus 1 over 100,000. Then we can multiply both top and bottom by 100,000, which makes the top just 73,826. And the denominator is going to be 100,000 minus 1. Which is 73,826 over 99,999. Now these both do have a another term in the nope, sorry. These do have a common factor of 3, so you should be able to get rid of the 3 very easily. Me personally, I actually like keeping it in terms of however, whatever numbers I have here that makes sense for the decimal itself. So like, I would want this as part of the answer at some point. Just me personally, I guess. Alright, so 73,826 divided by 3. Nope. Huh. Okay. Yeah, one number off. This has a remainder of 2, so oh well. Never mind. I just keep it like that. It's way easier to verify the answer. All right. Let's go raid somebody before I make any more silly mistakes. Oi. I don't appear to have too many people at this point. Okay, let's go see Pink Sapphire. She is playing New World and is the spouse of Buana, whom we have gone and raided on multiple occasions. So they're a really cute couple. I really like them. So we'll head on over there. I think they're probably playing together at the moment, but I didn't 100% pay attention to where everybody was. Oops. So, thanks everybody for coming. We're gonna come back on Friday, hopefully a little more rested, and probably play some more Final Fantasy VII Remake. Maybe do some more Elite Dangerous, because Boot Brigade just moved into Boot Brigade just moved into the place where we've been trying to move into for like years. So finally moved in. Now we've just got to establish ourselves as the dominant faction in the system. Shouldn't be too hard unless somebody's really fighting hard against us. But hope you all have a good rest of your week. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.